Good morning. We were implementing the negative feedback loop, and the prototype negative feedback loop has a loop gain, which is an integral, okay, which is an integrator, and that proportionality constant, that is the unity loop gain frequency, and that in the time domain determines how fast you reach steady state, and in the frequency domain it determines the bandwidth. In that ideal, I mean, in that prototype, the closed loop bandwidth is exactly equal to the unity loop gain frequency. But later, it turns out we'll have additional poles and zeros. Then, even then, the unity loop gain frequency is a reasonable first cut approximation to the closed loop bandwidth. Okay. So we start with the negative feedback amplifier. So in this, the loop gain is with omega u loop being omega u by k. This exact relationship, how omega u loop is related to the components in the circuit, that depends on the exact circuit. But the loop gain is this integral. Now, what does it mean? If you break the loop somewhere, okay, and then apply a step u of t and look at what comes back, and let's say you invert the sign because it is negative feedback. So the step response of L of S we know is a ramp. Okay, that's what this gives you, this business of continuously adjusting the output, and its slope is omega u loop. Now, what are all the problems that can come in? What we saw was that we can have a delay, that is, I'll show it in the feedback path. This has a transfer function exponential minus s td. Okay. So in this case, the unity, the loop gain is this times exponential minus std. Okay. And here we saw that I didn't show the full analysis. You can do it also. The closed loop response will be okay. It will be that one. And you can find the poles of this also. The denominator is not a polynomial. It has this exponential. But even there, okay, if the denominator goes to 0 for some values of s, those are the poles, right? And if those poles happen to be in the right half plane, that is, if the real part of s is greater than 0, that means the natural response blows up. If the real part of s is equal to 0, the poles are on the imaginary axis and the natural response doesn't die, but it stays at a constant amplitude. So the same rules still apply. So I won't, I mean, this can be analyzed with a little bit of algebra, but anyway, we can, I'll just summarize the result. In this case, it turns out that the step response, the closed loop step response, yesterday I had written it in different terms, but it's the same, right? If the sort of the time constant of this tau 0 is 1 by omega u loop. So everything is normalized to that, okay, delay and so on. So in this case, we have no overshoot and TD less than this, I mean greater than 1 by E and less than pi by 2 times the time constant, you will have ringing. This should be less than, but the system will be stable. This again, I mean, conforms to your intuition that as you go on increasing the delay, you will have more and more ringing, and you can even go to instability, because every time you go past the target, you go further and further away from the target. Okay, because in that delay, during that delay, you have moved a long way from where you should be, right? That's the idea. This is unstable. Now, of course, this ideal delay is not what you see in circuits. Okay, we have parasitic elements which cause something like a delay. Okay, so what really happens is you may have parasitic capacitance here. What it does is to introduce a pole in the loop gain. Okay, you can calculate the value of the pole. What will the pole be in this case? Assuming that this integrator behaves like an ideal voltage source, where will be the parasitic pole? So in any first order case, how do you find the pole? You find the effective resistance. I mean, eventually you can reduce the circuit to having only one capacitor or one inductor. And then you have to look at what is the effective resistance across the capacitor or the inductor. And from that you can find the pole. Okay. So these things you should be able to do intuitively. If you want, I mean, there is a, from your old course, the electrical circuits and networks, there is a assignment on first order circuits, right? With time domain and frequency domain responses, you can go through that and see. I mean, what you can do is you try to get the answer without deriving it, and then derive it and make sure that you get the same answer. That's how you build intuition. Okay. So first order circuits for piecewise constant inputs, you should be able to sketch the, I mean, write the expression for the time domain response and sketch it without any difficulty. Similarly, the frequency domain transfer functions you should be able to do. Okay. Yeah. For infinite delay, for infinite delay, it will take, I mean, it won't show at all, right? It will come with infinite delay. For infinite delay, I mean, there's no feedback. Okay. Right. That's right. Yeah. So here, the loop gain is of the form omega u loop by s, and in the denominator you have 1 plus s by p2. Okay. And the closed loop transfer function will be k, and you will have something of this sort. I won't derive this. These are all things you would have seen in your previous courses. I mean, the loop gain is second order now, right? So the closed loop system will also be second order. Okay, you can easily verify this, right? The key is that it's a second order system with some damping factor zeta. Okay, so here also you will see similar behavior, not exactly the same. So here, if you have zeta between, sorry, the other way around. You will have no overshoot, and If zeta is less than 1, you will have ringing. Okay. Now, in this particular case, it turns out it won't go into outright instability. That is, the natural response will always die out, but it will ring more and more. This is peculiarity of the second order system. When you go to higher order systems, that won't be the case. Now, what is the relationship between this model with the ideal delay and this second order case that we saw yesterday through the step response of the loop gain, right? So, if you sketch the step response of the loop gain, so in this case, you will see a ramp, ideal ramp, and in this case, you will see the ramp. This is the ideal, and the actual will be the same thing, which is shifted to the right by TD. Okay. And finally, when you have this one extra pole, what did we see? Compared to the ideal ramp, what was happening? It was similar, except it is smooth. It's not abruptly starting after some delay. But what was the horizontal displacement? It is 1 by P2. Okay. So that pole acts like a delay 1 by P2. Okay. Now, I will show simulations later. I am not sure if I have the pictures here. This is true, and I think this there was an assignment related to this in the third. There was a problem related to this in the third assignment, is it, or fourth one, where you had to calculate the step response of omega u by s times some complicated stuff. Maybe it's in the next assignment. You can work it out and see. So when you have many poles, what happens is every pole will add a delay like this. Okay, and it turns out these results are still roughly valid. Okay, that is, you want to keep the delay to be less than some value to avoid overshoot. Now, when you have multiple poles, all of them contribute to delays, and the same thing will still hold. Okay, is this fine? So, in general, with multiple poles, the delay is like the sum of all the extra poles. Okay. Right. So you can have either one pole at some frequency, or now you can also see each pole goes on adding a delay to keep the total delay the same. Let's say half of tau 0, half of 1 by omega u loop. If you have more and more poles you have, each pole must be at a higher frequency so that the sum is restricted to some value. Is this clear? You would have done the same things in the frequency domain, but I am showing you the time domain stuff. Is this part clear? You can tolerate a certain amount of delay in the feedback loop. If it comes from 2 poles, you can have apportion some delay to each one. If it comes from 6 poles, then obviously each one must have a smaller delay. So that means the poles themselves must be at correspondingly higher frequencies, right? So maybe you can tolerate 2 poles, both of them at 1 megahertz, or four poles, each of them at 2 megahertz, and so on. They will all have the same effect on the stability and ringing and so on. I'll show the simulations. You can simulate this and see in MATLAB or any other circuit simulator also. Is this okay? But this kind of intuition is important. You should know that when you are building the circuit, if you are introducing additional poles, basically you are introducing delays, and then that will compromise stability. Okay. Now, yesterday we also tried to, I asked what happens if you have a 0, for instance. We'll see how we could possibly get this. This is an idealized form. So again, what will be the step response in this case? I asked you to evaluate this, right? So this is the ideal step response. Okay. So what will be the actual one? What is it? Is it advanced in time, or what exactly happens? it is effectively an advance in time, but this is actually very easy to calculate because you have omega u loop by s, which is the original term, plus omega u loop by z1. Okay. So the step response of this is a ramp, the step response of that is a step. Okay. So you will get the step response to be, it will jump up, and this vertical displacement is just whatever is there, omega u loop by z1. So because of that, what is the horizontal displacement? It is that divided by the slope, and slope is omega u loop, so it is 1 by z1. Okay. So it's looks like time advance by 1 by z1. Of course, don't be confused by the term time advance. It's not non-causal or anything. Okay. Where it is ramping up, it looks like an advance. Okay. So this is again something you can use beneficially to improve the stability. So let's say you have a lot of delay, and possibly if you introduce a 0 somewhere in the loop, you could advance the step response and improve the stability. Is this okay? So this time domain reasoning is also important. The reason I like this is, first of all, this integrator model brings in the idea that you are continuously adjusting the output until the error goes to 0. That's what the negative feedback loop is doing. And in general, for a lot of cases, time domain reasoning gives you a lot of intuition, but it's not always easy to calculate. Okay, usually time domain calculations also tend to be somewhat messy. I mean, of course, in some cases they are easier, but they are somewhat messy. Okay, whereas frequency domain, generally the calculations are easier. On the other hand, it's a more abstract domain. I mean, all these transforms and so on. So you have to finally interpret the result to what happens in the time domain. Okay. So what would be your first idea? Let's say if you are presented with a problem, some signal and then some transfer function. So what comes out? How would you do it? Would you do it in the time domain or frequency domain? What would be your first approach? Frequency domain. Okay. So let me just show you one example. So let's say this is the transfer function. Okay. So this is h of s, and you have a square wave input. How would you solve this? You can try to do it in the frequency domain. So how would you do it in the frequency domain? What do you have to do to solve this in the frequency domain? Find the Laplace transform of this periodic signal. That's too messy, I think. Fourier series. Okay, what is the Fourier series of a square wave going from -1 to 1? Impulses at. So let's say the frequency of this is, I mean the period is t naught. Okay. So what will be in the Fourier series? Right. So what will be the component, right? What is the first component? Where will it be? So it will be at f naught. And what is the strength of that impulse? 4 by pi. Okay, this is something worthwhile remembering. You should visualize it also. The sine wave that best fits it is something like this. Its amplitude will be larger than the square wave. Okay, and the next one will be at 3 f naught. And what will be its amplitude? It will be 4 by 3 pi. Okay. So the first one will be like that. And the third harmonic, what happens is, it will do this. Okay. So it will sort of push up the sides and then push down the middle. That's how you get more square wave. Okay. So then that keeps happening. So anyway, fine. You can calculate all these components. Then what? Okay, so you have to evaluate this. So what is that? So this 4 by pi. So basically this whole thing can be written as summation of 4 by n pi cos n n omega naught t, right? For odd n. Okay. And what is the transfer function? That will be 1 by 1 plus j n omega naught by p1, right? That's the transfer function. So you have to multiply, essentially now you have to resolve this into real and imaginary parts. The real part gives you cos, imaginary part gives you sine, and then you add up all of that. Okay. So if I asked you to sketch the output waveform, will you be able to do it? If I asked you to sketch the waveform, how would you approach this problem? Is there an easier way? Okay, I see. So what will be, I mean, if you did it in the time domain, what will be the output? What will you get? This is a first order system, right? So it's like an RC, charge and discharge. You can immediately write that it will going to be like that. Okay. So there are cases where time domain is even easier. Okay. So because you can do all this, if you have a lot of stamina, you can sit down and write the summation and so on. But from that, you won't be able to recognize that the waveform looks like this. It's not easy. Okay. So be open to doing things in both domains. I mean, just because I said time domain, now don't start doing time domain for every problem. That's not wise either. Okay. So fine, zeros provide time advance and then poles have time delay. Now, how is this related to, how did you earlier analyze these systems, these negative feedback systems, whether there is ringing and so on, how much ringing should be there, etc. What was the approach? You used the frequency domain approach. What did you do? How did you analyze this negative feedback systems? Phase margin, etc., right? So what is that actually? Now, the thing is, first, there are stability criteria which tell you whether the system is stable or not stable. Okay. So that means the poles have to be in the left half plane for them to be stable. Okay. Now, as a designer, of course, that is important. You want the system to be stable, but you also want some measure of a margin. That is, you want to see how close from the edge you are before falling off, right? So that's why you have to have some notion of how much into the left half plane the poles are. Okay. So that is, of course, the once you say margin, there is always some vagueness because the required margin is different in different contexts. Okay. But that's the idea with these. That's the idea with having these margins. Okay. How do they come about? Again, I won't go into the details, but basically, the mother of all stability criteria is this Nyquist stability criterion. Okay. So if you have taken courses in complex analysis, you know that you can do lots of cool stuff with this transformations. So what you want is your, so you have the S plane, and in the S plane, you want your poles to be in the left half. Okay. So now it turns out that if you have some function f of a complex variable, okay. Now you evaluate this f on some closed loop, okay, and then this f itself is a complex number. So this is the f of s plane, okay. So obviously for every s on this curve, you evaluate this f and you plot it there, and you will get some other loop, okay, because this is going and coming back to the same point. That will also have the same thing. But how many of you have taken courses in complex analysis? Only one. Okay. So How many of you have, I mean, this Nyquist criterion was shown in what? Analog systems and lab and controls engineering, I guess, right? Huh? Controls. Okay. So what is the Nyquist criterion? What is the Nyquist criterion? Well, yeah, basically you can relate essentially whether, I mean, if this contour in the S-plane has poles inside, then this will encircle the origin, right? And also it will encircle it as many times as you have number of poles here. And if you have poles and zeros, it will be poles minus zeros, etc., etc. Okay. So now why is this useful for us? In any negative feedback system, I'll show this our example, but okay, the denominator will be of the form 1 plus L of S. Okay. So now what you want to do is to find out essentially whether this system has poles in the left half plane or right half plane, right? Or whether the denominator has zeros, okay? Whether the denominator has zeros in the left or right half plane. So what you do is the following: you form a contour like this, okay? So the contour that you choose is something, but that encircles all of the right half plane, and this actually has infinite radius, okay? So now if you use, I mean, this f of s will be 1 plus L of s, okay? So you calculate this along this contour, you calculate 1 plus L of s and see what happens to that contour, okay? So it should basically, if it encircles this or the origin, okay? So that means that there are some zeros of 1 plus L of s inside this contour, okay? Now, of course, instead of using 1 plus L of s, you can just use L of s and see, instead of encircling the origin, whether it encircles minus 1 comma 0. It's the same thing, right? So that is what this is. And of course, the encirclement has to be in the clockwise direction, etc., etc. Okay. So this is basically the Nyquist stability criterion. So if you use L of s, you look for whether this plot of contour plot of this is the L of S plane, right? L of S when it's evaluated on this contour. Okay. Now also the idea is that this semicircle at infinity, there L of S would have fallen off to 0. Okay. That's how it is, right? So that's why this always goes to the, in fact, I didn't draw it quite correctly. In reality, this will always go to the origin. Okay. Because L of S will fall off to 0. Okay. So this is correct for the previous case when I had the 1 plus L of S, but so you start from omega equal to 0 and then you go to omega equal to infinity, and along the way, if you encircle this minus 1 0, so that means that there are roots of 1 plus L of S in the right half plane. So this is what you try to avoid. Okay. So again, I won't go into the details of this. Now, some sort of shortcut for that is to say that but you don't typically draw the Nyquist contour like this. You can. How is it that you normally evaluate stability in circuits courses? What is it that you draw? Bode plot. Essentially, what is the Bode plot? It is the magnitude of this curve and the phase of that curve. You draw them separately. Okay. And you see when the curve enters the unit circle. Like I said, the loop gain always goes to 0 at infinite frequencies, right? So that means that this contour here, it will go to the origin, or the magnitude will always fall below 1 at some point. Okay. And you see where it goes inside the unit circle. Okay. So now you know that if it goes inside the unit circle in the second quadrant, so it must have crossed over like this and then it encircles minus 1, 0. That's the idea. Okay. So that's the idea behind this phase margin. But you have to be a little careful when you have zeros and so on. Okay. And you try to essentially, what is the business of the stability margin? The denominator should not become 0. That means L of S should not become minus 1. So the idea of this margin is you stay as far from minus 1 as possible. That's the margin. Okay. Is this fine? So in fact, you can use the magnitude of so L of S equals minus 1 for any omega. This means instability. Okay. So now this means keep L of S away from minus 1. Okay. This is the margin criterion. Okay. Of course, it should be stable to begin with. So that means no clockwise okay, it should be stable and it should stay away from minus 1. Now, how do you measure how far away, I mean, how do you measure whether it's away from minus 1? One is you just look at the minimum magnitude of this. Okay. This is fine. You can plot this. This is in fact called the stability margin. This will be, if you see some control system textbooks, it will be there. This is not what we typically use. We use what is called the phase margin. What is the phase margin? So basically, again, L of S at some S equals j omega equals minus 1. What does this mean? L of j omega is 1, the magnitude is 1, and the angle is minus 180 degrees. Okay. What is this phase margin? It is just telling you at L of j omega equal to 1, how far away are you from minus 180 degrees. Okay. The phase margin is if you introduce so much additional phase shift in the loop, it will become unstable. That's what it is. I mean, that also corresponds to your idea of margin, right? Okay. That is, if you are like, I don't know, 10 meters from the edge of the building. So if you go like 10 meters further, you will fall down. That's what this margin business is. Okay. So this is what you are familiar with. And what is a good phase margin to have? 1 degrees. So the thing is, it will be stable even if the phase margin is 1 degree. But the idea of margin is also some notion of robustness. So what is a reasonable phase margin to have? 45 degrees, 60 degrees. Yeah. So those are the, I mean, in fact, typically 60 degrees is given as a number. That is, if you're not told anything else, you design for 60 degrees phase margin. It's of course not always necessary to have 60 degrees phase margin. It can be too expensive in terms of resources. So I would say 30 degrees is also okay in some case, but probably not below that. Okay. So now we can try to reconcile this with our time domain intuition. I won't go too much into the phase margin business. You already know, right? The virtue of this phase margin is you are essentially evaluating the transfer function, the steady state transfer function, plotting the magnitude in phase, and then from that trying to figure out how stable you are. Okay. It's not whether you are stable, it's how stable you are. That's what the phase margin is trying to tell you. Okay. Now, what did our time domain stuff say? How much delay is okay? We said that to not have any ringing, which the delay has to be less than this. Okay. And of course, to have some ringing, it can be more. And then here you will have basically outright instability. Okay. So let's calculate the phase margin for this case. Okay. So now when the loop gain L of S is an integrator with an ideal delay. Okay. Calculate the phase margins for what is the phase margin when TD is 0? Please calculate it. This is actually a very simple calculation. Give me the phase margin for all these cases. What is the phase margin when TD is 0? Hmm? 90 degrees. Yeah. When the loop gain phase is always minus 90 degrees, and then how far is it away from minus 180? Okay. What is the phase margin for all those other values? Right. Okay, take a calculator. Okay, take a calculator. What is the unity loop gain frequency? Okay, loop. It doesn't depend on the other factors, right? And then what is the angle of this function? What is the angle of this function? is the angle of the comp? Yeah, so it's complicated. You can write down where are all the tan angles. Where do you learn it? Oh, yeah. What I observe is a total lack of stamina for calculating numbers. This won't work. Okay. So in engineering, knowing means calculating. Okay. So what does it mean to know a circuit? I mean, is it knowing how to draw a circuit or recognizing it? That's also part of it. But the most important part of knowing is how to figure out how the circuit behaves in some circumstance. Okay. So if you don't have the stamina to calculate, it's a big problem. Okay. So first of all, what is the angle of this? So we have to calculate the angle of L of S at what frequency? At the unity loop gain frequency. And in this case, of course, omega U loop itself is the unity loop gain frequency. Okay. So what is this? S equals j omega U loop, sorry. So this will be minus pi by 2 from the first part minus omega U loop times Td. Okay. So that's all that's there to it. How much is the phase margin? How far this is away from pi. So this it's the phase margin. That's all. Okay. So the phase margin, sorry, pi by 2 plus that. The pi by 2, the phase margin is pi by 2 minus omega U loop Td. Okay. So here it is pi by 2 or 90 degrees. And what is it in this case? 69 degrees. This is 61 degrees. And here 0. Obviously, it is unstable, right? That is the case where you have a sinusoidal natural response. Okay. So it has to come out to be 0. Okay. So, but this calculation you should be able to do much faster, right? And of course, you can do the calculation only if you start doing it. I mean, staring at the page will not make the calculation happen. Okay, that may be a favorite method of solving, but it won't work. So please put pen to paper and calculate the numbers. Okay. And symbolic stuff is good, but many times in engineering you have to calculate the numbers, and it will be messy. It will have decimal places and so on. Okay, don't always expect some neat fractions with small numbers and things like that. Okay. So now what is this telling you? So for instance, earlier we said that a delay of about half of the ideal time constant is okay, whatever that means. And now this is consistent with your earlier idea, right? That is, it gives you some around 60 degrees phase margin. Okay. So this, I think with this, you should be able to reconcile the time domain and the frequency domain pictures. You can have excess delay, right? You don't have to aim for 90 degrees phase margin. You will later see that it becomes too expensive in terms of power dissipation and so on. Okay. Because, or if you think about it, you will later see that to get 90 degrees phase margin, you know that the parasitic poles, the additional poles have to be pushed out well beyond the unity loop gain frequency. And to do that, you will end up spending a lot of power. Okay. So there is no point over designing this either, right? So you aim for whatever is the appropriate phase margin under the circumstances. If you're not given any information, this excess delay of half of the time constant or around 60 degrees phase margin, that is okay, right? Is this fine? So with this, I think you can you should be able to reconcile the frequency domain stability criteria that you earlier knew and the time domain stuff that I showed. Of course, you calculate using whatever you want, but this what the time domain stuff gives you is intuition, right? You know why a delay causes overshoot and potentially instability, right? And how much delay is tolerable. Basically, you naturally, I mean, the ideal system has some time constant, which is 1 by omega u loop. Some fraction of that is what is tolerable. Okay. Is that fine? And if you have too much delay, what can you do? The only thing is increase the time constant also so that you go more slowly. That is, you reduce omega u loop. So by reducing the bandwidth, you can always stabilize it. May not be desirable, but possible. Okay. Any questions? So you can also calculate how much delay it is for, let's say 30 degrees phase margin and so on. Okay. So you can obviously tolerate like more delay, but you can't go too much more than that. Okay. 1 by E. Yeah, that the calculation is a little more messy, but you can get that. So there also, if you basically, okay, for the second order system, how do you get this? That is zeta equal to 1 is critical damping, right? So what do you look for in the transfer function? What is it that you look for no overshoot and the ringing case? What? Yeah, basically, you look for cases where you have complex conjugate poles or only real poles, right? When you have complex conjugate poles, you will have ringing. When you have only real poles, you will not have ringing. Okay. So as you change the value of zeta, at some point you have that repeated pole case, and if zeta is lowered below that, you will get the poles will split into complex conjugate parts. So you can do the exact same thing here. So you can essentially you find the zeros of this, right? This denominator. And if you look for the condition where you have only real poles, you will find that that's the case, that you will get that same condition. Okay. So that can be done. I mean, you just put, if you may ensure that S is real, you will get some condition. Okay. It's slightly more messy, involved algebra, but not too complicated. Any other questions? So now, of course, we'll build negative feedback systems. Those are everywhere. And to build a negative feedback system, this is not necessary. I mean, we will have other types also. But to build this standard type of negative feedback system, what do you need? You need some way of computing the error. And integrating the error. Okay. So these are what you need. So basically, the combination of these two is available as a standard block. This is the op amp. Okay. So the op amp, basically, what is the op amp? Op amp has two inputs, right? And then it has a certain parameter omega u. That is the most important parameter of the op amp. Okay, this omega u. So what it does is it takes the difference between these input voltages and integrates it with a proportionality constant omega u. That's what the op amp does. Okay. So this combination of differencing and integration, that is the op-amp. So now we have to build it using the components that we have on a CMOS process. Okay. So how would we implement it? How would we implement integration? What is the, I mean, we have to do this now with circuits, right? So what are the components that will allow you to do integration with respect to time? What is that? So basically the two components that give you integral relationships are a capacitor and an inductor, right? The capacitor basically says that the voltage is integral of the current, and for the inductor, the current is an integral of the voltage. But of course, for practical reasons, we can't make large inductors at all, right? Whereas we can make very good capacitors. Okay. So we will be using only capacitors for this. In principle, you could have used inductors, but in practice, you almost always it's not possible. Okay. So we will use inductors. On the other hand, this the input to the op amp is a voltage, and what the capacitor integrates is the current. So what do you have to do? You have to convert this voltage to a current. So how do you do that? You use a transconductor, you use a GM stage. That can be done. Anyway, every MOS transistor effectively converts a voltage to a current, and you pass that current through the capacitor, and you get this integrator. Okay, so that is your op amp. So we'll go from there. Any other questions?